Alright, so we talked about continental drift and some of the ideas behind geology in the last couple of sessions. And we're going to continue talking about important geologic concepts today. We spent a lot of time talking about continental drift and the continental plates. And there are a couple of forces at work here that drive the shape of these continental plates, and the geologic activity takes place among them. Among other things, you have the idea of diastrophism. Diastrophism is the pressure activity on continental plates that deforms them by folding, twisting, warping, breaking, or compressing rock. Warping, breaking, fracturing. Folding, compressing. And all sorts of things you can do with solid rock. And remember, what we're talking about here is solid rock, but you put under enough pressure for long enough, you can do all sorts of things with it. And just kind of, for example, suppose this was a continental plate. You put enough pressure on it, it's going to bend and fold and warp. It just depends on the different pressures on it. And since this rock is brittle, yes, it will fracture in parts of it as these pressures are put on it, creating fault lines as they bump up against each other, and as they fold and break and twist and compress in between. Got here the textbook, page 52. Got, so you can see where some of this activity is taking place. This is where the diastrophism is taking place here because of this earthquake activity. Folds, and these folds creating mountains and so forth here at the edge of the Pacific plate and so forth. Now, I got the idea here also of volcanism. This is the force that transports magma or heated gases towards the surface. Comes from the idea of volcanology, the scientific study of volcanoes. It's a branch of geology. Sometimes these gases rise to the surface and explode. So I have, like, say, Mount St. Helens. Well, I didn't have a lot of lava spewing from it because it was a volcano. It was mostly just a gas plume coming up. The superheated gas has caused a lot of mudslides and a lot of flooding because of basically it's melted all the ice and snow around the area. But you go to volcanoes and say like in Iceland or in Hawaii, well, it's just lava is kind of spewing all over the surface. That's because molten rock has been pushed up through these little flumes. Actually, the book gives a pretty good example here. On page 53, figure 3.9, kind of what some of this diastrophism causes in terms of volcanism. Particularly, look at the idea of subduction. Continental plates being pushed over and being pushed underneath another plate. That's what we see where the North America and Asian plates are meeting the Pacific plates. The Pacific plate is going under North America. It's also going under the Asian plate. So you got where these two plates meet. There's a lot of folding and everything there. So that also does is it causes one plate goes down. That's called subduction. And of course, it's moving into the mantle where everything's superheated. So what happens? This rock melts. But because it's melting, because their gas is kind of trapped as it goes down, what happens? They start coming back, bubbling back up. And this magma and this gas, that creates upward pressure on the surface rock. So for Mount St. Helens worked in 1980, they noticed this huge bulge in the mountain where you can see some of this superheated rock and gas and magma was kind of pushing at the side of the mountain. But volcanism, that's the process of how mountains grow. Not all of them, but some of them. Some of them quite dramatically. But again, because these plates are pressing against each other, that's causing the rocks to bend and fold upward. So you tend to have a lot of mountain ranges at the edge of where these faults meet. Famous example, California, Rocky Mountains, St. Andreas Fault, where the Pacific and the North American plates are meeting. They're kind of squeezing against each other. So what's that done over millions of years? Push the surface up, creating the Rocky Mountains. And since the Pacific plate is moving underneath of it, what's happening? All that magma and gas moving upward, creating occasional volcano here. Doesn't happen very often on the Pacific plate, but on the North American plate, but there are a few active volcanoes here and there. But active is in terms of, an eruption every couple hundred years, maybe. Nothing that really happens very often. Now, you also have the idea of warping. Not as in Star Trek, but as in twisting and folding. Twisting of this, the different layers and the different rocks and the different continental plate as these kind of come into contact with each other. Example, Cape Cod is caused by warping. Great Lakes is caused as an example. Cape Cod is an example of warping. Great Lakes is an example of warping. The Atlantic coast, there's a lot of down warping, kind of this sloping it downwards. So because of this down warping, it's caused a number of irregularly shaped estuaries. Estuaries are wetland, basically swamp. and underwater canyons. Now, the degree of folding, of course, depends on amount of time and the composition of the rock that's being pressed on. So you see an example here, again on page 53, the example right here. So we'll see that kind of strata here, have a kind of meandering gentle hill, or have a very sharp series of hills. All because of pressures of the continental plate. Because remember what geology is, it's what it all comes down to is pressure and time, but also composition. All these different forces working together. Now, in the compressional pressure caused by the plate movements, as great layers of rock are forced to buckle. Because remember, they can kind of fold and bend and compress a little bit, but it's still rock, it's still brittle, it's still break. So this may be a warping or bending effect, and a ridge and a series of parallel folds may develop. Remember though, it's not this continental plates that necessarily cause hills in an area. There can be other forces at work, erosion, like in our area. Some of these hills are caused by the gas pressure by oil formation beneath our feet, kind of causing several areas to kind of rise up and form hills. Next, along fault lines, you have sometimes you see something called an escarpment. An escarpment is this very steep slope, sometimes several hundred miles long and several hundred feet high. It's just almost like a huge ridge. But this can go on for a couple hundred feet high, but it can also go on for a couple hundred miles. Very distinctive landform. And we talked about the idea of the Rift Valley. Particularly in East Africa, in Kenya, where Eastern Africa is starting to split apart from the rest of Africa. You'll see these huge, basically holes in long holes here, as periodically as surrounded by hills, as the continents kind of push each other apart, kind of along the fault line here. But you can see these kind of rifts and gaps and kind of fissures, sometimes for several miles, going off and on for several miles. But with our all these different plates and everything, and these different layers of rocks, you can see these layers of rocks as they build up over millions of years. An example here is presented in the book. Example here in Maryland, Maryland, Pennsylvania area here. basically you see where the highways kind of cut through these hills sometimes. And you see these kind of layers of rock built in, sometimes in different patterns, or because it's easier sometimes just to cut through the rock rather than just have cars go up and over and up and over again. But what you can see though there is several million years of warping and diastrophism at work. Millions of years of geologic history before your eyes. You can especially see this in areas like where the new interstates kind of come in at far northwestern Arkansas, the Missouri border. You see a lot of it here across western Texas, central western Texas. A lot of it in New Mexico and Arizona, where they kind of cut through the rock. But you can see these examples, these different breaks and so forth periodically. Because sometimes of these, especially these downward sloping patterns, is an example of a lot of erosion having taken place as well. So there might have been some very large hills here at one time, but they just eroded away. And basically have the small one kind of left behind. Now I talked about earthquakes and the damage they cause on land, but what about at sea? There are a lot of earthquakes that occur underwater. And what happens is these earthquakes can cause huge waves that can carry for hundreds of miles. Of course, what we're talking about here is the tsunami. It's a Japanese word because Japan, being so geologically active, has so many earthquakes, they've seen this phenomenon a lot. Basically, it's like, well, like suppose you drop a huge rock in a piece in a water and watch the waves form because of it. The waves are reacting to a disturbance in the water. It takes a while to kind of go back, for kind of settle back in. Same thing happens with earthquakes at sea. There are massive tsunamis often because all that water's been disrupted and has to settle back into place. And of course, you see these waves form and rippling and generally evening out. There's a lot of disruption in the meantime. They used to be called somewhat inaccurately tidal waves, but they're really not. It's often much more severe. There's a huge waves created at sea, usually by underground earthquakes. And here's basically what you got. You got your earthquake, happens here at sea. Rock dropping, shifting around, causing this massive wave to reverberate across the area. And the thing about a tsunami is it's usually not seen out in the open sea. The effects are really only seen as you get closer to the surface. So you got this kind of undulating waves here, but as they get closer to the surface, where that wave pressure and everything kind of starts building as you get closer to the surface, and we get closer and taller and until finally, these huge waves crashing inland. So the surge of water pushes forward, it pushes far inland. And it'll just keep moving in, riding up and up and up. But there's a funny thing about tsunamis is you have this massive little earthquake here at sea. A lot what happens usually is first the water will rush way out. And then it'll come way back in really fast. After earthquakes in Japan, tsunami warnings are routinely broadcast across the nation, usually highlighting areas of the home islands that are most likely to be affected. Tsunami watches, warnings, and so forth. And across the Pacific Ocean area, there are warning and tracking systems in place. I found this again. There are systems of sensors and observations systems in place to watch for tsunamis. So in the Pacific area, there's not a lot of danger as long as you pay attention to what's going on and you are able to get close to an area's relative safety. But fortunately, though, you got areas like the Indian Ocean, which are relatively poor and for many years did not have this system in place. Gave us one of the worst tsunamis in history, December 2004. An earthquake off the coast of Indonesia created a tsunami that moved westerly across the Indian Ocean, approximately 50 feet in height. But it has silently crept across the ocean, crashing into India and Bangladesh and all the way across to Africa. 240,000 people died. So June of 1896, severe one in Japan after a major earthquake there. It's measured at 29 meters using the metric system. Actually, the equivalent about 85 feet or something like that. Led to 27,000 deaths and led to Japan creating that system of tsunamis and warnings. May of 1960, off the coast of Chile, a 10-meter tsunami left 1,250 dead. And in July of 1998, New Guinea, a 15-meter wave left 3,000 dead. The thing is, sometimes once these crash into the coast, and these coastal cities are very low lying, there's nowhere to go if you haven't paid attention to warnings. So people try to run into taller buildings, but sometimes even these buildings just start flooding or washed away by the pressure of the water. Like I said, the tsunamis can extend for thousands of miles. Now, volcano types. Back to volcanism. Got two classic forms of volcanoes. First is the stratotype, also called a composite volcano. These are often steep-sided cinder cones formed through a great explosion. Basically, it's a classic where the magma rises up to the top and explodes at the top. Kind of the cinder cone shape. Mount Rainier in Washington is an example. Then you have what they call a shield volcano. They often form without explosions. And often it's not a very tall mountain, it's usually long, gentle slopes. You have like a shield, kind of, somebody laying a shield down on the surface. That's kind of magma going up and kind of oozing out everywhere. Mauna Kea in Hawaii is an example of a shield volcano.